Hello everyone and welcome to Vibrations in Acoustics. Today we're going to do a rotational spring mass system and we're going to find the steady state response for this system. It has a force applied to it, it has a forcing function applied to the end, so we're going to have to do a relation with that. But overall, when you're setting up one of these systems, you see a rotational system, you automatically go to sum of the moments in order to start making the equation of motion. So in this case, sum of the moments, we're going to assume that theta is very small, because in order to find this displacement right here, it would normally be sine theta times a sine theta in order to determine how far that is. But for a very small theta, sine isn't really necessary. So for the moments, we're going to do k negative k1 a times theta, which is the displacement x basically right here or right here. And then in order to make it a moment, you multiply it by the distance again, which is a. And we're assuming negative, so we're assuming by the right-hand rule that this rotation is negative, this rotation is positive. This will be a little bit useful later on in how we set it up. It doesn't really matter, you can assume these either directions you want to, but it just makes the math work out a little bit cleaner here at the beginning. Okay, and then for the other moment, we have negative k2 b times theta times b, and then plus ft times L, because L is the total distance to the forcing function over here, is equal to J naught theta double dot, which is the standard output of any sum of the moments. It has to equal this. This has to be the total force. Okay, so now solving, getting all the thetas onto a single side, we end up with J naught theta double dot plus K1, collecting terms, a squared, plus K2 b squared times theta is equal to L f of t. And now, completing all this out, I'm going to remove this picture here just to bring up this page some more. Now, J naught is equal to theta dot plus, we'll just call this KEQ up here because that's what it is. This is the equivalent spring constant of the system, times theta is equal to L F naught sine of omega t, which is the forcing function if you look at the previous picture. Okay, so looking at this, we have KEQ. We can get that from the spring constants that we're given. We have F naught, we have omega, we have L. We need to find J naught in order to completely solve this problem. Okay, so in order to get J naught, you have to take the J of the mass, the large mass in the system, the block basically on the end. We have large M and then small m, plus J naught small m, which is the mass of the bar. The mass of the block is pretty easy. It's just ml squared, the mass times the distance from the point of rotation squared. The bar is a little bit trickier because it actually takes two separate pieces because of these springs attached to it, which basically represent other rotational points. So the first part of it will be 1/12 ml squared, which is the standard equation for a bar rotating about its center. So basically assuming right here at the center of mass, if the bar is rotating theta, then you take 1/12 ml squared. But then you also have to add in the fact that there's another spring right here that the bar could potentially rotate about. And that creates m.25 L squared. And the 0.25 is this distance right here, which is actually the distance A. You got to kind of look back at your picture earlier in the video to see that. But yeah, in order to get the actual rotational moment, or the mass moment of inertia with this set of springs, you have to do basically the rotation about this spring and then the rotation about this spring as referenced from this rotational point right here. It's a little bit confusing. If you don't see that, go ahead and review mass moments of inertia. But if you finish this out, you'll get a J naught is equal to ml squared plus 1/3 ml squared. So now J naught is equal to 50 kilograms times 1 meter. 1 meter squared plus 1/3 times 10 kilograms times 1 meter squared, which is equal to 53.33 kilograms per meter squared is equal to J naught. All right, so we have that. And now in order to solve for KEQ, because we're eventually going to need that in order to solve for omega n and other stuff, KAB using this, where is it? This piece right up here. Basically taking this and solving it out to get KEQ. That will give you 5,000 newtons per meter, which is the K for both of those springs. Both K1 and K2 are equal to that, so you can basically factor it out. Times 0.25 squared plus 0.5 squared. And this will equal 1,562.5 Newton meters for your KEQ. Now omega n is equal to the square root of KEQ over J naught, which is then equal to 1562.5 all over 53.333 square root of all that stuff will equal 5.413. We need to convert omega because it is in RPMs right now. So omega is equal to 1,000 RPMs, which is cycles per minute. And in order to do the conversion on that, you have to multiply it by 2 pi over 60, because there's 60 seconds in a minute. And there are 2 pi radians in one complete cycle of rotation. This will give you 104.72. And then R is equal to omega over omega n. And you can sub in those values, they're right there, 19.346. So then, in order to solve for the amplitude of the system, because we know that for a standard rotational system, a spring mass system, sigma s of t, which is the response, is equal to QSS, or this, you might have seen this as XSS, but since we're in a rotational system, I'm going to use Q, sine of omega t. That's the equation we're going for. So we have omega, we're looking to solve QSS. So in order to do that, we need R, because QSS is equal to delta ST all over 1 minus R squared. And you should have been shown this equation before. If not, look at one of my previous videos or anything like along those lines. This displacement is equal to L times F naught over K, and K is basically the spring constant of the rod. The force is the force by the forcing function, the maximum amplitude, and L multiplied by F naught over L is the moment. So in order to find the displacement of a bar that is rotating about some point, some fixed point, or just standard point, if we were looking at the bending of the bar, then it could be a KEQ that way too. So that's what this is. The displacement is based on the moment over the spring constant of the system. Okay, and this is over 1 minus R squared. So if we solve QSS, I'm going to move this down here, this equation down here. It will be equal to 1 meter times 500 newtons, because we know F naught is 500 newtons, because it was given in the problem, divided by 15562.5, and divide that by 1 minus 19.346, which is R squared, and this will equal negative 8.573 times 10 to the negative 4th radians. So now Q for the static case, the response of the static case, or theta SS of t is equal to negative 8.573 times 10 to the negative 4th sine of 104.72 t radians. And that is how you solve for the steady state response of a spring mass rotational system.